We are going to continue on with our discussion of acidity and what it means. But just to put this in a little bit of context, remember that all of this, we're not just interested in acids and bases. A lot of this is motivated by a question that was asked last time, which is related to why and how reactions happen. Last time we considered something like this substitution reaction, where the negatively charged oxygen, lone pairs on that oxygen, attack the sigma star of the weak carbon iodide bond. They attack at carbon, you make a new carbon-oxygen bond, and you break the carbon iodide bond. And this is going to be a major type of reaction that we'll see. In fact, the first big reactions we talk about are going to be examples of this kind of reaction. And somebody asked, how do I know whether this reaction is favorable? And there's two basic concerns here. The first is, what is the strength of the bonds that you broke versus the bonds that you formed? That's issue number one. And then issue two is going to be the stability of the negatively charged oxygen nucleophile versus the stability of the I-, which we have called before, is sort of the leaving group. It's the thing that gets swapped out for the nucleophile. Here's the nucleophile, and then here's the leaving group. And if you take into account these two things, you can get a sense for whether the reaction's favorable or not. We'll deal with strength of bonds formed versus bonds broken in chapter 6. That part's pretty easy. We'll deal with the stability of this negatively charged oxygen, this molecule that we call an alkoxide, versus iodide, starting today. And it's a little bit roundabout. We're going to rationalize the stability of the alkoxide versus the iodide by thinking about the acidity of their conjugate acids. And this is something I mentioned last time. So for example, if I were to draw the conjugate acid of the alkoxide, it's this molecule called an alcohol. If I were to draw the conjugate acid of iodide, it's HI, okay? Two different molecules. Now, I can look up their pKa's, and I told you last time that pKa is a measure of how acidic something is. And if pKa is lower, that means the acid is stronger. So the pKa of HI is like -11. So that's more acidic than HCl. That's very, very acidic. In contrast, the pKa of the alcohol, if you look that up, is around 16. Now this is one opportunity to be able to compare which is more acidic, right? What do you think? HI. Well, okay, something that has acid in its name is probably more acidic than something that doesn't, right? So hydroiodic acid, probably more acidic than the alcohol. And look, it's more acidic not by 27, whatever that means. That's 27 pKa units. That's log units. So 10 to the 27 times more acidic. That means if this is more acidic, that means that its conjugate base is more stable. That is a key relationship we're going to use pKa information for. Strong acids have very stable conjugate bases. All right, strong acids have very stable conjugate bases. This alcohol is less acidic than HI, and therefore its conjugate base, the alkoxide, is less stable than I-. Do you follow that reasoning? Yes?
Sorry, this is unrelated, and maybe you'll get this, but will we need to memorize any pKa's?
Yeah, you'll memorize 2 pKa's, and I'll tell you what those are. Yep. All right, just to preview, we're not only going to rely on pKa's because we don't want to be robots that just look up numbers in tables. A computer can do that. What we want you to be able to do is rationalize why something might be more acidic than something else, and also rationalize why a conjugate base might be more stable than another conjugate base. So let's just try that out with the alkoxide versus the iodide. You'll see that most often it will be easiest to explain which compound is more acidic, which acid is more acidic, by instead dealing with which conjugate base is more stable. So when you're looking at two conjugate bases, you want to think about first, what is the atom that has the charge on it? Okay, so in the alkoxide, it's oxygen. On the iodide, it's iodine, right? And the principle that you want to remember in terms of conjugate bases, what are things that could make conjugate bases more stable? There's a few. One factor is delocalization. And another factor is electronegativity. We'll see that delocalization you can break up into sort of two categories. One is size and the other is resonance. And then electronegativity is a pretty straightforward argument. So we will see, and I'll give you some examples of this later. We're not going to delve into it too much now, but when there is a difference in size, atomic radius between two atoms, usually the larger atom will be more stable with a negative charge on it. And that's just a simple consequence of delocalization. Iodide happens to be quite a bit larger than oxygen. If you want to see how that's true, I'll just open up the Spartan app and I'll just draw some molecule with an oxygen on it. So this is just going to be a simple alcohol. And you can see the size of oxygen there, right? And if we turn this into space filling, you get the idea that oxygen's a little bit smaller than carbon. Incidentally, that trend, size trend for atoms in the same row of the periodic table also agrees with electronegativity. The reason oxygen is a little bit smaller than carbon is because oxygen's nuclear charge is larger and it tends to hold the electrons a little bit tighter. And that's actually the same reason that oxygen's more electronegative than carbon. Now, if we switch the oxygen to, say, iodide, you can see the carbon-iodide bond is longer, and you get the idea that maybe iodide is larger until you look at the space filling, and then you're like, yeah, it's like enormously larger than oxygen. So we're not looking at something that has a negative charge on it. We were just looking at the alcohol versus the methyl iodide. But the idea is that iodide is larger and the alkoxide, the oxygen, is smaller. Therefore, the iodide spreads out its negative charge through a larger area of space. The negative charge is more delocalized and therefore more stable. Do you follow that reasoning? When there's a difference in size, and we're only talking about the atom that bears the charge. We're not thinking about the size of the whole molecule, just the atom that bears the charge. When there's a difference in size, we don't even have to worry that much about electronegativity. Okay, I- is a more stable conjugate base than the alkoxide, therefore HI is a more acidic molecule than the alcohol. All right, does that make sense? Yes?
How do we know if the size difference is large enough that delocalization takes precedence over looking at electronegativity?
So how do you know if size difference is large enough that delocalization takes sort of precedence over differences in electronegativity? Where there is a size difference, I can't think of an example where it doesn't matter more. For example, the other comparison you might do is this alcohol versus HCl. Chlorine and oxygen have similar electronegativities. So if electronegativity were the major factor here in acidity, you would think that HCl and the alcohol would be similar in acidity and that their conjugate bases would be similar in stability. Nevertheless, the pKa of HCl is -7 and the pKa of the alcohol is 16. So, and chloro is not that much bigger than the alcohol, but than oxygen, but it's big enough to make a difference. Here's, nope, that was carbon. Here's the chlorine. We'll do space filling of chlorine. And just have in your mind, imagine in your mind sort of how big that is, and now we'll switch it to oxygen, and you can see that the oxygen is quite a bit smaller. So where there is a size difference, we're talking about one row, and this is really, I know some of you want to know precise size difference that matters in angstroms versus precise electronegativity difference in whatever number, and have some sort of function that offsets both of them. Nah, we're not going to do that because that's math, and we like math, but not that much. If it's from a different row of the periodic table, size matters more. Okay, so with that, let's go to a pKa table, and we'll start to illustrate some of these trends. So this is an actual copy of the pKa table that's on your problem set, and that will be on your exam. People always want to know what kind of pKa table is going to be on the exam, and this is it, folks. Behold, or sorry, I need my Doofenshmirtz voice. Behold, the pKa tableinator, right? That's not bad. I could have done better. I needed to warm up, but yeah. Okay, these pKa's are listed in order of acidity. Notice that the pKa values towards the top of the table are pretty negative, whereas the pKa's towards the bottom of the table are really positive, very high, okay? Low pKa means most acidic. High pKa means least acidic. Now this is a good time as any to tell you that we're going to dispense with something that you learned in Chem 105 or 106. I don't remember which one it was. I've heard that some of you memorized a list of strong acids and strong bases. And the reason you did that is you didn't know this at the time. I told you that strong is always relative. And the list of strong acids that you memorized were acids that were strong enough that they would lose their protons to water. You interpreted that in terms of 100% dissociation, right? That the proton was going to be gone. But I've told you that that was an oversimplification. The proton doesn't just float off into wherever. It gets removed by water, right? So remember that pKa in general is derived from this equation where we compare an acid in strength to where we have asked the question, will an acid lose its proton to water? Notice that the proton doesn't float off into nowhere. It gets removed by water following this basic pattern that we've showed you. Lone pair electrons on oxygen attack the sigma star between hydrogen and whatever it's bonded to, and you end up with this product. pKa essentially tells you how likely that is to happen. So we're gonna, because all of the acids on this list have been compared to water, and because the pKa values come from that comparison, we're gonna lose the worry about is it a strong acid or strong base as though it's an absolute term. We're just gonna ask, is this acid stronger than this one? Or is this conjugate base more stable than this one? Do you see how it's always gonna be a relative term? So if you ask me, is that a strong acid? I'm going to say, I don't know, relative to what? You give me a comparison, then I can answer the question. If you don't, I'm not that interested. Okay, yes?
Just going back a little bit, could you give an example where electronegativity is the factor used to determine?
Yep, we can do that right now. Question was, when is electronegativity the dominant factor? Okay, so when you're comparing acids within a row of the periodic table, let's just pull a few from this list. I see one here. This describes the acidity of the following. This pKa of 50 describes the acidity of this proton. Essentially, we're talking about an sp3 hybridized carbon-hydrogen bond, okay? And the conjugate base of that is, maybe it would be good to draw in some of the hydrogens that are implied but not shown. The conjugate base, what would be left behind if a proton were removed from that acid, is this negatively charged carbon. We'll call this a carbanion. Now you're told that that pKa is 50. Carbon, notice, is next to nitrogen on the periodic table. So let's go find a nitrogen-containing compound. And here we are. This is a pKa for neutral nitrogen, ammonia. We'll call this an example of an amine functional group. And its conjugate base is this negatively charged nitrogen with 2 lone pairs on it. This is called an amide anion. Okay, that pKa is 38. Now we could make a comparison already, but let's just keep going. Let's look at the oxygen-containing analog. There's a lot of options, but and none of them are on the list because this is one I want you to memorize. I'll draw this alcohol, and we'll look at its conjugate base, which you've seen before because we talked about it at the beginning. This is called an alkoxide. Negative charge is on the oxygen. And that pKa, and this is one to memorize, so I'm going to put the asterisk on it for memorize it, is 16. Notice, alcohol is more acidic than amine, which is more acidic than this molecule, which is called an alkane. You're going to start to learn what some of these molecules are called. Somebody out there has the question, do you want us to know those? Is that why you're writing them down? Well, you're going to learn about molecular nomenclature in chapter 3, so yes. For right now, your goal is to just understand the lecture. Okay, so when I say this amine, if you have an idea of what I'm talking about, that's useful. One more that we'll put on this list is the fluorine analog. So let's put HF on the list, and its conjugate base is F minus. That sounds like a grade that you want to avoid. And thankfully at BYU we don't have Fs, so there you go. That's not funny to all of you. You're worried about that, aren't you? That's fine. The pKa of HF isn't on this list, but it's around 4. Okay, so HF is most acidic. The alkane is least acidic. That means F minus is most stable, and the carbanion is least stable. Another way of saying least stable is most reactive or strongest base. And another way of saying most stable is least reactive and weakest base. Okay? And this follows electronegativity of the atom that bears the negative charge. F minus is most, and this is my abbreviation for electronegativity, most electronegative. And then carbon in this list is least electronegative. Now, why does electronegativity matter here? And the reason it matters is atomic size doesn't vary as much within a row of the table. So if you're comparing atoms that bear the negative charge within a row of the periodic table, the most important factor is going to be electronegativity. If you're comparing atoms within a column of the periodic table, the most important factor is going to be size. Okay? Yes?
I kind of have a specific question about a conjugated base.
Sure.
From the book. So why is CH2 double bonded to CH2, not the conjugate base of CH3 single bonded to CH2?
Okay. I think I know where you're getting that from. I should maybe look it up quickly to see if I got it. And the short answer is I think you're right, and I'm not entirely sure what the book was going for there. Let me just... Yeah, so I think you're looking at problem 2.3a, where it gave you this, and it asked you, is this the conjugate acid of this? And the answer is unequivocally yes. And the reason for that is, first, if a base like water removed this proton, electrons could kick down and form a pi bond there. Now that's an example of a reaction you're not going to get to until chapter 7 or 8. But they wanted you to think about that. The other reason you can think of it as the conjugate acid is you will see in chapter 10 that the pi bond can actually attack the sigma star between hydrogen and whatever it's bonded to, and that will give you this product. So yeah, it should be the conjugate acid. If the book says no, I have no idea what they're doing. Okay, so a few more things, about pKa. I'm gonna just move this down because I need more space to talk about what's on the table. And I'll just, for comparison and completeness in the notes, I'll put the relevant pKa's by the, relevant acids. So you getting the idea that a really strong acid has a very stable conjugate base, and that a really weak acid has a very reactive conjugate base? You're getting the idea that we're explaining acidity by drawing the conjugate base and examining how well it stabilizes negative charge? Okay, good. Another example that's not sort of on this list where size matters more than electronegativity is to look at the series of the halogen acids, HF versus HCl versus HBr versus HI. And the pKa's, you could look them up in a table, are around 4, -7, -9, and -11. Most acidic, least acidic. Oops, why am I drawing least down there? That's weird. Least acidic. So that's true even though F-, even though fluorine is most electronegative. Iodide is least electronegative. So this is an important point. You're trained, in your mind, you want to jump to electronegativity first and say, okay, if fluorine's more electronegative, that means it should pull the electrons closer to itself. Therefore, the hydrogen shouldn't be held as tightly, and therefore HF should be a really strong acid. But that is exactly wrong. Okay? It turns out that bonds between hydrogen and carbon, and then on the other side, atoms that are electronegative, are really quite strong. I told you we wouldn't deal with bond strength today, and we really won't. We're going to deal with that in chapter 6. But honestly, the more electronegative an atom is when it's bonded to a carbon, the more stable the bond is. There's some reasons for that we can talk about. So the HF bond is quite stable. The HI bond is not very stable at all. And the reason has to do with size. So even though these, F minus being most electronegative, even though that is true, it's not relevant to explaining what's going on. And that's also the case for, iodide being the least electronegative. The thing that does matter is that iodide is largest and you get best electron delocalization. How do you spell that? I can't spell that. Delocalization. And therefore, I minus is more stable. Okay? Smallest, most localized, and so on. So it's going to take a little bit of practice because you're gonna be thinking about electronegativity when you haven't thought a lot about atomic size. Yes?
So size matters most until it comes to the oxoacids, right?
Size matters most until it comes to the oxoacids. I'm not sure what you mean by that.
Acids with oxygen in it.
Okay, so size matters when comparing things down a column of the periodic table. Electronegativity matters when comparing atoms that are in the same row of the periodic table. It's not just an oxygen or a halogen thing. I can give you another example where size is important. Here is the alcohol, and here is the sulfur version of an alcohol, which is called a thiol. The pKa of the alcohol, as you know, is 16. The pKa of the thiol, if we found it on our list above, it's in the table, and it's right there, that's 8. So you can see that the thiol is more acidic than the alcohol. And if you look at their conjugate bases, again, you've got alkoxide versus the negatively charged conjugate base here, which is called a thiolate. Sulfur is bigger, therefore you have better electron delocalization, and therefore the thiolate is more stable than the alkoxide. Follow that reasoning? Yes?
Can you also follow the trend, the more acidic it is, the stronger the conjugate base will be,
The more acidic something is, the stronger the conjugate. This is where you get mixed up. You got to pay attention while you're talking. When I'm talking to myself here. The more acidic the acid, the more stable the conjugate base is, or the more weak the conjugate base is. Yeah. Yes.
How would you determine molecules that have the same atoms, like isomers, for example? Like, how would you determine which one's more acidic than another?
So isomers, how would you determine which one is more acidic than another? I can't think of an example off the top of my head about isomers, but I can give you some examples where the atom that bears the negative charge is the same, but there are other structural features that explain why something is more stable. Is that all right? So we'll just take, this is ethanol. This is the classical alcohol that we've been showing. And then here is a different acid. This is acetic acid or vinegar, okay? One of these gets people drunk, the other is kind of tart, and if you need to clean off hard water stains, you can do that. So they're clearly different. The pKa values are 16 and 4. So which one's more acidic? The acetic acid. And again, if it has acid in its name, then it's probably more acidic. Let's talk about why. Let's draw the conjugate bases. Again, the alkoxide. The alkoxide has the negative charge is at least held on an oxygen. if you look at the conjugate base of acetic acid, it is this molecule that we're going to call a carboxylate. In this case, we would call it the acetate anion. Now, can you see a difference between those two? Oxygen holds the negative charge on both of them, so there's no electronegativity difference, but what else do you see? Possibility for resonance stabilization, and if you didn't recognize that, notice the pattern. Lone pairs adjacent to a pi bond. It tells you that you can do this. The two-step pi bond negative charge interchange, where oxygen 1, lone pairs on oxygen 1 now form a pi bond with the adjacent carbon, and the pi bond on the other oxygen moves out onto that oxygen as a lone pair. This negative charge is in two places simultaneously. In fact, if we were to draw the hybrid structure, you would see that that negative charge is evenly shared between the two oxygens. Resonance delocalization is stabilizing. Okay? Resonance delocalization is stabilizing, therefore, acetate is the more stable conjugate base, and therefore, acetic acid is more acidic. And the point is that the negative charge on the alkoxide is localized, not stabilized by resonance. Okay? Now, some of you might have been tempted to look at that and say, well, acetate's a bigger molecule than the alkoxide, therefore shouldn't size be the explanation? The answer is no. The issue of size is never about the size of the whole molecule. It's always about the size of the atom that holds the negative charge. And in this case, it's the same. It's both oxygens. Okay, so don't misapply the size thing. Let me show you another example where resonance matters. I'll just put this other item on the list. We'll just keep it in the same comparison as with the other oxygen-based acids. This is a special kind of alcohol, and this is called phenol. You don't need to know that, but I'm going to call it that. Its pKa is 10. Now, see if you can figure this out. Phenol doesn't look like acetic acid. It looks more like ethanol, but you can see that phenol is what? More or less acidic than ethanol? Okay, better figure that out. Lower pKa means more acidic, okay? You're gonna make that mistake in the same way that I forget which hand is my right hand versus my left hand. The first shot, I always get that wrong. Something's backwards in my brain or something like that. It's genetic. My grandpa used to have to, my grandma would say, Dale, throw a rock, when he needed to figure out what his right hand was. He could remember if he throws a rock with his right hand, that's the right hand. Anyway, yes, phenol is more acidic than ethanol. Do you see, by the way, why it's pointless to ask, is this a strong acid? Well, relative to what? Is phenol a strong acid? Well, it's stronger than ethanol, but it's not as strong as acetic acid. It's just a relative comparison. Can you think of a reason why phenol is more acidic than ethanol? Draw the conjugate base. Don't just stare at me, draw it. Okay, you got it? It's got a negative charge on the oxygen. what do you notice about that negative charge? What's it adjacent to? A pi bond. So that's a classic case where resonance stabilization is going to be a thing. So I will draw one of the resonance structures that shows the negative charge on the oxygen being delocalized. There are two others which you should also be able to draw. If you were to draw all of them, you would conclude that this negative charge is delocalized onto those atoms as well. Now, why? So resonance explains why phenol is more acidic than ethanol, because the charge is delocalized by resonance here, whereas it's localized for the conjugate base of ethanol. Now, here's a fun question. Compare the conjugate bases of acetate versus the acetate versus this conjugate base of phenol, which we will call phenolate. Phenol is clearly less acidic than acetic acid. Look at their conjugate bases. Why? Can you justify that? Could you explain that? They're both stabilized by resonance, and in fact, the phenolate has the negative charge delocalized in more places. So what's the difference? Somebody want to take a crack at that? Commit to it? Go ahead.
Oxygen is more electronegative and can better handle a negative.
Right, so you notice that in acetate, the other atom that bears the charge is oxygen, also an oxygen, whereas in phenolate, the other atoms that bear the charge are carbon. Oxygen's more electronegative than carbon, oxygen better bears the negative charge. Do you follow the reasoning? Looking for differences? Okay, good. These are the kinds of decisions that you'll need to be able to make. We have some more. Do we dare? Trying to figure out what I want to do. Yeah, while we're on the subject of more acidic and less acidic, let's do this. Sure, no. All right, fine. Let's compare these two acids. This is acetic acid. Again, vinegar, you can put that on your salad dressing. Its pKa is 4. And you've seen the conjugate base, and it's acetate, and you know that it is resonance stabilized. Here is a relative of acetic acid. This is called trifluoroacetic acid, because instead of having hydrogens on the adjacent carbon, trifluoroacetic acid has fluorines. And this pKa is 2. If you put vinegar on your salad dressing, you're going to feel tart. If you put trifluoroacetic acid on your salad, your tongue is going to burn. And nobody does that. So let's talk about why. Let's look at their conjugate bases. There's clearly no difference in the atoms that bear the negative charge in either resonance structure. You should be able to see, I'm not going to point it out here by drawing the other resonance structures, but you should be able to see how both oxygens share the negative charge by resonance. There's no difference in the atoms that bear the charge. There's no difference in the resonance. What difference do you see? Yeah, fluorines versus hydrogens. Now, why should those matter? They're not even the atoms holding the charge. And the idea here is that nearby electronegative groups have an impact. So let's just zoom in on trifluoroacetate. You know that fluorine is more electronegative than carbon, right? So this is a symbol that maybe was used in 105, 106 to talk about bond dipoles. You ever seen that before? The arrow points towards the atom that's more negatively, has more of a partial negative charge. The little plus points at the atom that should have a partial positive charge. So can I use that? You guys are great. It's the same as delta plus, delta minus. So you got 3 of these, each of the fluorines pulling electron density away from the carbon. That makes this carbon electron poor, it in turn pulls electron density away from the adjacent carbon, which can in turn start to pull electron density away from the negative charge. In other words, fluorine causes the electrons in the sigma bond, the electrons in the sigma bonds, both carbon-fluorine and carbon, to lean toward the fluorines. That ends up if you pull electrons away and they lean towards the fluorines, that should stabilize this negative charge by decreasing electron repulsion. It's going to decrease repulsion with the negative charge of the conjugate base. We call this sort of electron tug-of-war an inductive effect. We're not actually moving the negative charge from the oxygens, but we're making it less bad for it to be there because the rest of the electrons in the molecule are leaning towards the fluorine, and that sort of stabilizes the negative charge. So this inductive effect is an example of a form of delocalization. It's not resonance. It happens because of the electronegativity of the nearby atoms. Again, don't mess this up. You're going to think electronegativity. It's not the electronegativity of the atom that bears the charge. It's the presence of nearby electronegative groups that are allowing the electrons in the molecule to lean away from where the negative charge is. I'm sorry, every time I hear the word leaning, you guys ever watch While You Were Sleeping? If you haven't, it's really kind of fun. I mean, this is a late 90s film, so it's been almost 30 years. But yeah, there's a part at which Joe Fusco asks Sandra Bullock's character, "Hey, Luce, is this guy bothering you? Because it looks like he's leaning." Meaning, I think Riz is the word you guys use for it now, but I got nothing. Okay. Back to the pKa table. I just want you to become familiar with this. The pKa's to memorize are the following: water and alcohols. And by alcohols, I mean where the conjugate base is not stabilized by resonance, have a pKa of 16, and their conjugate bases are hydroxide or the alkoxide. The other one I want you to memorize is H3O+ and protonated alcohols, and again, where their conjugate base is not stabilized by resonance, and that pKa is -2. Those are the two that will not be on this list. Everything else is on the list. Couple of warnings about using this table. Some of you should practice ahead of time, not just assume that it's going to make sense on the exam, because some of you will make the following mistakes. First, notice there are some molecules that appear to show up twice on the list. So these are amines. What is the and I'll just draw you an example of what this is. What is the conjugate base of this acid? What would it look like? Lose a hydrogen, and then what? Okay, not bad. This is called ammonium, an ammonium ion, and this is called an amine. Notice that the ammonium is a cation, positively charged, and the amine is neutral. The neutral amine is the conjugate base of the ammonium cation. Now, here's the trick. Notice that the neutral amine is also has a pKa because the neutral amine has a conjugate base that is now a negatively charged amide ion. So we'll call that the amide anion because it's negatively charged. So some of you are going to use the wrong pKa. And that's question? No, you're just saying probably me. Yes, good. Awareness is the first step, right? We've all done it. Let me show you an example where you could misapply this information. So let's draw an equilibrium. I'm trying to figure it. Sure. Let's ask whether the following can happen. Sure. Let's just do this. Let's make it as bad as we possibly can. All right. So I'm going to ask the following question. Where does this equilibrium lie? And I'm going to draw the conjugate acid and the conjugate base. Okay. In this equilibrium, we're proposing that the nitrogen from the amine attacks this hydrogen and then the electrons go on to that nitrogen. This actually gives you a chance to use the use this pKa table, because you'll look at this molecule and that doesn't look very much like an amine. You might look at that and say, what pKa should I use? Just go to the table and find the right one. Find one that looks as much like this as possible. It's actually right here. I'm hurrying us along, but if you looked, you would find it. And what is that pKa? It's about 6 or 7. You know what? I told my 17-year-old. I've now. I don't get it still, but I know how to make the jokes. And I told my 17-year-old that when I am making the jokes, the meme is well and truly dead. So I truly do not get it. But I walked downstairs. The 17-year-old was with a bunch of his friends, and I said, "What are there, 6 or 7 of you here?" And they were like, And then, all right, we're going to go get a soda. We'll be back in 6 or 7 minutes. I will tell him how you reacted to that. He'll get a kick out of that. Yeah, the pKa is 6. Sorry. This is the acid on this side of the equation. Over here, the acid is has the pKa of. Now, find the right one. Which is it? Which pKa should I use, 11 or 38? 11. Okay. So now you've identified the acids on either side of the equation. You ask which acid is strongest. The one with the lower pKa is strongest. The strongest acid loses its proton, so equilibrium should favor this. Okay? Now, if you got mixed up, if you chose the wrong pKa, it turns out, it looks like in this case, even if you got the wrong pKa, you would have been fine. Dumb example. Dang it. Suppose you had chosen the wrong pKa for this guy. Do you see how you could have got the wrong answer? All right, I will have a better example next time when we start. Get out of here. I'll see you on Friday.